the complexometric titration. Okay. So during our teaching activity in the chemistry of equilibria, we realized that the Edta is a strong complexing agent. Okay. And it works better at alkaline pH. Okay. So let's read now the procedure, and then I will explain you all the steps in order to understand what you are doing. Okay? So this fill the burette with the solution of a DTA standard 0,1 molar. It's easy because you find it on the bench, on the shelf. Okay, no problem. Okay, just be sure that the burette is clean. Okay. Now, using a volumetric pipette, just read it together, okay, of 25.0 milliliters, okay, take this amount of volume, okay, of calcium chloride. Now, you can ask me, why calcium chloride? Because the calcium chloride is soluble. It's a soluble compound in the water, okay? But not calcium carbonate. The dolomites are made by calcium carbonate, okay? So this is, as you can read, titration test. It's a trial, it's a demonstration, just to see the variation of the indicator from red, purple, purple, red to blue, okay? So it's just a test. So you will find a bottle with a solution of calcium chloride. As before, don't pick up your solution directly from the bottle. Okay, take a small beaker, just put some solution, and then use the volumetric pipette to pipette 25.0 milliliters. Okay, then transfer it in the conical Meyer flask directly. Okay, then dilute 100 milliliters. Try to make almost the same dilution. Okay, in order to better appreciate the difference in color. Okay, and now add. This is a crucial point, but is something that you have just to think as a chemist, as pharmaceutical chemist. Okay, 2 milliliters of a solution of magnesium Edta. Now, just think of the reaction. Okay, so you will have Edta that will react with the calcium in your titration, okay, to make a complex. Now you can ask why you are adding a solution of magnesium Edta. Because magnesium as calcium is complexed by Edta, okay? But adding the same amount of magnesium and Edta, nothing will change, because we are adding, yes, a compound that will compete with the calcium, like magnesium, but we add the same amount, the same equivalent of Edta, and so nothing changed. Then, another question, okay, but why you do this? No, it's normal, no? This is something strange. We do this because the variation in color, okay, by this indicator, the heliochrome black T that you will find there, okay, is not so good if you use only calcium, okay, because the variation, okay, in color is made by the indicator. So the indicator is a complex agent, like Edta, okay? But has a property to change color when it gets calcium or magnesium. So when it complex, is blue. When it's not complexing anything, is red. Okay? So if you add a small quantity of this indicator, okay, and then you start the titration with the DTA, okay, then you will have, okay, a blue color, a red color at the beginning, because this complex indicator, calcium or magnesium, okay, makes the color red. So when you add a DTA, so the DTA goes in the beaker, in the flask, and look there and say, okay, what there is there? Okay, there is calcium in high quantity, okay, and then it starts to complex calcium, and then you continue with your burette to add the calcium, to add the DTA and DTA, and the amount of calcium will decrease, no? Till the ending point, okay. So at the ending point, okay, there is no calcium anymore, okay, and so what happened? That the indicator will get the magnesium that is in solution, magnesium and DTA, okay? But when you start again to add more DTA, the magnesium, okay, will be captured by the DTA and then leaves the indicator, okay? So this variation in color, okay, with magnesium is much faster than calcium, okay? That is the reason, okay? So you will have a change in color using the magnesium and DTA faster, okay, than calcium and DTA, okay? Because the indicator does not like to release calcium. So because of the complex between the calcium and the indicator is much stronger than indicator magnesium, okay? So first the DTA capture all the calcium in solution, okay? Then when calcium there is anymore, I mean it's the small equilibrium, there isn't anymore, then capture the magnesium. So the magnesium that is at the end with the indicator, okay, will be released and the indicator will turn from red to blue. That is the reaction, okay? So, but you don't worry about this. You just add this 2 mil, about 2 mil, not so precise, okay, with your pipette, okay? 2 milliliters of this solution, magnesium and DTA. Then 5 milliliters, just read, 5 milliliters of ammonia buffer. Also in this case, 5 milliliters, 4 or 6 is the same. Okay, it's not precise, this amount. Why we add ammonia buffer? We add ammonia buffer because the DTA è mezzogiorno di fuoco. Ehi, non so lei. Sleeping. So why ammonia? So the ammonia buffer
works better alkaline.
Exactly. Because the titration is performed at alkaline pH. Because the DTA, you remember, DTA Y4 minus, okay? That is at alkaline pH, the only one that is able to make a complex with calcium. So we need an alkaline pH in order to make the complex of calcium and DTA. Okay? And these 3-4 drops, okay, 4 drops, let's say, of this heliochrome black tea, which is an indicator. Maybe on the bench you can find it as a net. Nero heliochrome tea for the Italians, okay? Our heliochrome black tea, okay, for the others, okay? And so all these reagents are there, okay? Now, so with this test, so you will see the variation of your indicator. So you have to do it very fast, okay? So you see the variation from red, purple, red to blue, okay? And that's all. Then fill again your burette, okay? Only one shot, That's all, okay? You want shot, don't waste your time. Because you need more time this time than the previous one. Okay, why? Let's read the titration of the unknown sample. Okay? So now, anytime you perform a titration, you have to go to the balance and weigh a quantity of 250 milligrams, okay? Approximately, but with high precision, as you did last time, okay? Last time you did between 0.3 to 0.5, remember, with the analytical balance. Now, approximately 150 milligrams, so it's 0.25 grams, okay? So, okay, this is important. Don't stay nearby the balance, starting and adding it to reach exactly 250 milligrams. You don't find it. You have just to stay in a range of the 250. Okay? Then quantitative transfer, as you did last time, in your conical flask, nella belta, okay? You have to bring to volume because you weigh exactly, okay? Okay, and then you add 20-30 milliliters of distilled water, okay? And then 2 molar, okay, drop wise, sono io. Luca, sto a lezione, ci possiamo sentire dopo. Ti richiamo io. Okay, let's finish. Okay. Now, this is another point that should be clarified. Why? Because we add distilled water, and that is okay. Now you read it, just read with me. 20-30 milliliters of distilled water. Then 2 molar chlorhydric acid or hydrochloric acid, drop wise, drop by drop, until the complete dissolution of your sample. Why? Well, because your sample is mainly, okay, is a calcium carbonate. Okay, so calcium carbonate, as you should know, okay, so CaCO3 is a low soluble compound. So what happened in acidic media? So CaCO3 plus HCl, so 2 HCl goes to Ca. Okay, let's write first what happened here. 2 CO2 or H2 CO3 is better, plus CO3 plus 2Cl minus, okay, or it should be calcium plus Ca2 plus. Okay, this is what happened. So the dolomite will dissolve with the acid rain. Okay, that's what happened. And so you get H2CO3. Okay, this is what is present in the mineral water, because H2CO3 at high temperature is dissolved, is not dissolved, is dissociated in CO2 plus H2O. Okay? Because of the equilibrium of this Okay? The equilibrium of this, okay, is